If you've ever seen footage of houses being torn apart by hurricanes, you might have noticed that roofs are not blown over as you would expect, but rather seem to be lifted into the air. Using some simple physics, we can show that, indeed, the roof gets blown out from the inside out, due to the air underneath the roof. Let's first model the problem by making some approximations. Consider a house with a flat roof, measuring 6 meters wide and 13 meters in length. Then we assume that the hurricane wind blows horizontally over the roof with a velocity of 130 kilometers per hour, or roughly 80 miles per hour. Given only these pieces of information, the question will be whether the roof comes off or not, and if it does, how, since the wind is parallel to the roof's surface. Before we dive headfirst into the calculations, we will first outline a strategy to solve this problem. Since we are dealing with a fluid in motion, the wind, what should come to mind is Bernoullis' principle. It states that when the velocity increases in a fluid, the pressure inside will decrease. And since the wind rages over the outside of the roof, we expect there to be a drop in pressure. Therefore, a difference in pressure will arise between the inside and the outside of the roof, and this in turn results in a net pressure from the inside to the outside. Then we remind ourselves that a pressure exerted on a surface leads to a force, and thus we reason that it will be this force coming from the air inside of the house that will blow off the roof. Let's now use this strategy to calculate what force the roof must be able to withstand to survive this gust of wind. Step 1 is to use the Bernoullis principle to calculate the drop in pressure due to the large velocity of the wind. The formula relates the pressure and velocity of the fluid by stating that a specific combination of fluid properties will be constant. This formula can be seen as a form of energy conservation, and thus it can be used as such by comparing two scenarios and equating their respective left-hand sides of this equation. In this case, we compare the inside of the roof with the outside of the roof. Inside, the pressure is simply the atmospheric pressure. There is no significant motion of the air, so its velocity is zero and the second term can be dropped. The third term relates to the depth underneath a surface, which is not relevant here, but we copy it either way. And this sum of terms has to be equal to a constant c. Outside, we have the unknown pressure P, which is modified by the velocity of the wind. Again, the third term we simply copy. Also, these terms need to sum to the same constant c. Since both left-hand sides are equal to c, they have to be equal to each other. We can merge them in one equation, which we then need to solve for the pressure difference, P atmosphere minus P. We also see that these irrelevant terms containing H drop out, since they are the same for both scenarios. Then, bringing P to the other side, we find the expression for the difference in pressure in terms of the velocity. Filling in the numbers, where we convert from kilometers per hour to meter per second, we find 785 kilogram meter squared divided by meter cubed times second squared. But what is this unit? It should be a pressure with units of pascals. And this is a good sanity check to see whether we made any mistakes. To get pascals from this unit, we first simplify it, cancelling out powers of meter. Pascals are equivalent units to newtons per square meter. But what do we do with this kilogram we have? Well, Newton is a unit of force, and the most famous formula with force inside is Newton's second law. And we can now use the units of this equation to find that 1 Newton is equal to 1 kilogram meter per second squared. Therefore, dividing both sides by m squared to get pascals on the left-hand side, we indeed find that the units we obtain from our calculations are indeed pascals, and so things check out. Now that we have the difference in pressure, we can calculate the force that corresponds to it. This force is simply the pressure difference multiplied by the area we're talking about. For us, this area is the surface of the roof, 6 meters by 13 meters, which is 78 squared meter. And the pressure we calculated to be 785 pascals. Multiplying them, it gives us an end result of 61,230 newtons of force that act on the roof, even though the wind is blowing horizontally or parallel over it. Now this force is enough to lift a 6,100 kilogram roof. Now I don't know anything about roofs, to judge whether that's enough or not. So I will leave that to more qualified people. And this is how we solve such exercises. If you enjoy it, give it a thumbs up, and I will see you in the next one.